We declared the Voyager mission complete in 2012. The press releases were written. The headlines ran. Humanity's first interstellar spacecraft had crossed the boundary of the solar system, and that was the story. The problem's that the data kept arriving, and the data didn't match. Not in small ways, not in ways that required minor adjustments to the models. The plasma density on the other side of the boundary was 40 times higher than the predictions. The magnetic field didn't rotate the way it should have. The energetic particle counts dropped and rose in patterns that none of the pre-crossing simulations had anticipated. And the spacecraft itself, this object we launched in 1977, this machine built with the computing power roughly equivalent to a modern pocket calculator, kept transmitting, kept measuring, and kept sending back numbers that the people who built the models couldn't immediately explain. This is not a story about a successful mission. It is a story about what happens when the thing you finally reach turns out to be nothing like the map you drew of it. Voyager 1 is currently moving at roughly 17 kilometers per second relative to the Sun. That is not a metaphor or an approximation. That is the actual measured velocity, updated continuously by the Deep Space Network, the array of radio dishes that still locks onto a signal so faint it arrives at Earth with less power than it would take to dimly light a single pixel on a phone screen. After more than 47 years of travel, the spacecraft is roughly 24 billion kilometers from Earth. If you tried to drive there at highway speed without stopping, it would take approximately 26 million years. The signal traveling at the speed of light takes about 22 hours to make the one-way trip. We know where it is. That part is not in question. What is in question is what it has been moving through, and what that says about everything we thought we knew about the edge of the solar system. To understand why that matters, you need to understand what Voyager 1 actually was. Not the mission you remember from the commemorative documentaries, the actual thing. In the early 1970s, a young aerospace engineer named Gary Flandreau was working at the Jet Propulsion Laboratory, which is operated by the California Institute of Technology on behalf of the space agency. He was assigned a routine task: calculate trajectories for potential outer planet missions. He sat down with the orbital mechanics and found something that hadn't been widely noticed. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune would align in a configuration that occurs once every approximately 175 years. A spacecraft launched at the right moment could use each planet's gravity to slingshot to the next, a technique called gravity assist, and visit all 4 outer planets in a single trajectory. The window was narrow. Launch had to happen between 1976 and 1977. Miss it, and the next opportunity arrives in the middle of the 22nd century. Flandreau was 25 years old when he figured this out. He wrote it up, submitted it, and the calculation changed everything. The mission that became Voyager was designed around that window. 2 spacecraft, Voyager 1 and Voyager 2, launched 16 days apart in 1977. Voyager 1 took the faster, more direct trajectory that would carry it past Jupiter and Saturn and then curve upward out of the plane of the solar system. Voyager 2 took the slower path that would eventually reach Uranus and Neptune. The popular history frames this as triumph, and it was. Jupiter's Great Red Spot photographed in detail for the first time. Io's volcanoes, active, erupting, a moon more geologically violent than anything in the inner solar system. The complexity of Saturn's rings resolved from distant smear into structure. These were genuine revelations. But something else was happening simultaneously, something that received less attention in the press. The scientists weren't just photographing planets, they were measuring the space between them. Charged particle detectors, plasma wave instruments, magnetometers, low-energy charged particle analyzers. These instruments were reading the environment continuously, not just during planetary encounters, and the data they returned was building a picture of a region of space that no human instrument had ever sampled before. The solar wind, the continuous stream of charged particles flowing outward from the Sun, was the medium Voyager was moving through. Physicists had predicted its behavior with reasonable confidence. The sun pushes this wind outward in all directions at between 300 and 800 kilometers per second. At some point, far from the sun, this outflow must slow down as it encounters the interstellar medium, the thin gas and magnetic fields that fill the space between stars. The slowdown was expected to produce a shock wave, a zone where the solar wind abruptly drops from supersonic to subsonic speeds. This was called the termination shock. Beyond the termination shock, the theory predicted a region called the heliopause sheath, a turbulent zone where the slowed solar wind piles up and mixes chaotically. And at the outer edge of this region, the boundary where solar influence ends and true interstellar space begins, the heliopause. This was the model. It was built over decades by some of the best plasma physicists in the world. It was supported by indirect measurements, by observations of other stars' analogous structures, by the mathematical framework of magnetohydrodynamics. It was not a guess, it was a serious scientific model with genuine predictive power. Voyager crossed the termination shock in 2004. The instruments measured the slowdown, the particle counts changed, the magnetic field behavior shifted. Everything worked approximately as expected, and that was supposed to be the confirmation. Edward Stone was 76 years old in 2012, and he had been the project scientist for the Voyager mission since 1972, a tenure that by that point spanned 4 decades and represented one of the longest continuous scientific responsibilities in the history of space exploration. He was sitting in his office at the California Institute of Technology when the data started coming in from Voyager 1's crossing of what the team believed was the heliopause. Stone had spent years preparing for this moment. The models predicted what should happen at the boundary. He was watching the numbers to see if they matched. The charged particle data looked right. Galactic cosmic rays, high-energy particles from outside the solar system, increased sharply. Solar energetic particles dropped. This was the signature the models predicted. In August of 2012, the team announced Voyager 1 had crossed into interstellar space. The heliopause had been identified. The solar system had an edge, and humanity had crossed it. The announcement was genuine, and the data was real. But the press conference was also, in a specific technical sense, premature. The magnetic field didn't rotate. This is the detail that matters. When a spacecraft crosses from the heliosphere into the interstellar medium, the models predicted that the direction of the dominant magnetic field should change. The Sun's magnetic field and the interstellar magnetic field are not aligned. At the heliopause, you should see the field direction shift. It did not. The field strength changed, the particle populations changed, but the direction stayed the same for months after the crossing. Stone acknowledged this at the time. He didn't hide it, but the nuance got lost in the coverage. The headline was, "Humanity exits the solar system." The asterisk was, "But the magnetic field isn't doing what we said it would do, and we're not sure why." Here is what I find genuinely unsettling about this, not as a rhetorical device, but as an actual fact about how knowledge works. The Voyager team didn't discover that their model was wrong because of a dramatic failure. The spacecraft didn't stop transmitting. No instrument broke. The mission worked flawlessly. The model was wrong because it worked well enough to get to the boundary and then failed at the most important moment, the actual measurement of the thing the model was built to predict. 40 years of theoretical development, and the field direction was off. That's not a catastrophic failure. It's something subtler, a model that was adequate for predictions, but inadequate for precision. Don Gurnett was a plasma physicist at the University of Iowa who designed and built the plasma wave science instrument on Voyager 1. In April of 2013, his team published a paper announcing that they had detected oscillations in the plasma around the spacecraft, oscillations that, when analyzed, indicated the local electron density. The density was roughly 40 times higher than pre-crossing predictions, 40 times, not 40%, a factor of 40. Gurnett's team had been waiting for the right kind of solar event, a coronal mass ejection from the sun, a burst of particles that would travel outward and interact with the local plasma, causing it to ring like a struck bell. The ringing produced the oscillation signal. The signal gave the density, and the density said that everything the models had predicted about the interstellar medium in this region was wrong by an order of magnitude. The heliopause, the zone between the termination shock and the heliopause, had been modeled as a relatively smooth transition region. It turned out to be far more complex, far more compressed in some places and extended in others, and the interstellar medium just outside the heliopause was far denser than predicted. The models had been built partly from observations of other stars, partly from theoretical extrapolation, and partly from the assumption that the local interstellar medium was relatively uniform and well characterized. That assumption was wrong. There's a specific kind of vertigo in this. We built a model of a place. We sent a machine to that place. The machine arrived and took measurements. The measurement said the model was wrong. And the uncomfortable part is not just that the model was wrong. It's that we cannot go back and rebuild the model easily, because the model was wrong in a region where we have exactly one data point, the trajectory of a single spacecraft moving at 17 kilometers per second through a sample of space smaller than an atom compared to the full extent of the interstellar medium. This is the thing I keep returning to, and I'll say it plainly. We used our best physics to predict what the edge of the solar system would look like, and the universe simply did not cooperate. Not spectacularly, not catastrophically, just quietly. The numbers were different, and that gap between prediction and measurement is the actual location of our ignorance, not some vague philosophical admission that science is imperfect, but a specific quantitative gap that sits in the published literature and refuses to close. There is another anomaly that predates the crossing and remains partially unresolved. In 2002, Slava Turishev, a physicist at the Jet Propulsion Laboratory, published a detailed analysis of an anomalous acceleration affecting both Voyager spacecraft, as well as the Pioneer 10 and 11 probes. All four spacecraft were moving slightly slower than the models predicted, not much slower. The discrepancy was tiny. A deceleration of roughly 8.74 times 10 to the negative 10 meters per second squared. A number so small it's easier to describe as the weight of a single human hair pressing against the back of the spacecraft continuously for decades. This was the Pioneer anomaly, and for years it was cited as a potential signal of new physics, modified gravity, dark matter effects, some force not accounted for in the standard model. Turishev was skeptical. He sat with the Pioneer data for years, working through the thermal models of the spacecraft, the way heat radiates from the electronics and the nuclear power sources and pushes on the spacecraft like a tiny asymmetric force. When he finally completed the thermal analysis in 2012, he concluded that the anomaly was explained. Heat radiation from the electrical systems was producing a tiny but measurable thrust in the direction opposite to travel, slowing the spacecraft slightly. The thermal solution is the accepted explanation. But here is what it costs. It means that modeling the thermal behavior of a spacecraft accurately enough to account for a force this small requires knowing the precise state of every component, every surface, every angle of radiation. And the Pioneer spacecraft were built in the early 1970s with documentation that was incomplete. Turishev spent years reconstructing what could not be directly measured. For Voyager 1, the thermal situation is different. The spacecraft was better documented, the power sources are known, the current power output is tracked. But Voyager is also in a different environment than Pioneer was when the anomaly was most precisely measured. And the question the Pioneer anomaly left behind is not whether gravity is modified, that explanation lost, but rather how well we actually understand the thermal and radiation environment at these distances. The short answer is well enough to navigate, not well enough to resolve anomalies at this level of precision without years of analysis. Meanwhile, Voyager 1's power is declining. The radioisotope thermoelectric generators that convert the heat from decaying plutonium into electricity were providing about 470 watts at launch. They decay predictably. By 2023, they were producing roughly enough power to run a conventional light bulb, around 33 watts. Instruments have been shut down one by one as the power budget has contracted. The plasma wave science system, the cosmic ray subsystem, the low-energy charged particle instrument, each shutdown reduces what we can learn. There's a particular kind of scientific failure that doesn't look like failure. The model predicts a termination shock. There is a termination shock. The model predicts a heliopause. There is a heliopause. The broad strokes are right. The specific numbers are wrong. And the specific numbers are wrong by amounts that matter. A factor of 40 in plasma density is not a rounding error. It is a structural failure in the model of what the heliospheric boundary is doing to the material around it. This pattern, the broad structure, correct, the specific predictions wrong, is not unique to space physics. It is the normal condition of science at the edge of what has been directly measured. Every model is built from the data available, and the data available is never a complete sample of the environment being modeled. The model extrapolates, and where it extrapolates, it fails. Not always, not catastrophically, but at the precision level that matters for the next question. The spacecraft team made a difficult decision in 2023 that illustrates exactly how much is at stake. An unplanned code execution, the flight computer running a corrupted chip, sending the wrong command sequence to the transmitter, caused Voyager to lose contact with Earth for 5 months. 5 months of silence from an object 24 billion kilometers away. The team traced the problem, identified the corrupted memory location, and worked out a solution. Route the affected code around the bad chip, storing it in different memory locations and patching the data back together at transmission. They executed this repair across a 22-hour one-way signal delay. The repair worked. Contact was re-established in April of 2024. The spacecraft resumed normal operations with fewer working instruments, but still transmitting. Think about what that means, mechanically. A machine launched 47 years ago, running on hardware that is by any modern standard ancient, suffered a memory corruption failure in deep interstellar space, beyond any model of the environment we had developed, and a team of engineers and scientists, some of whom were not born when Voyager launched, diagnosed the fault, designed a repair, and implemented it across a communication gap of nearly a day. That is the actual human achievement of the Voyager mission. Not the photographs, not the crossing of the heliopause, the fact that we are still in contact, still learning, still fixing hardware across the distance that light takes 22 hours to cross. But here is what the repair also revealed. Voyager 1 is running on borrowed time, and every instrument that goes offline represents a question that will go permanently unanswered. The spacecraft has perhaps 3 to 5 more years of scientific operation before power levels drop below what is needed to transmit data. After that, the transmitter shuts down. The spacecraft continues moving. It will cross into the Oort cloud in about 300 years. It will approach the vicinity of another star in roughly 40,000 years. But we will hear nothing. The record of interstellar space that Voyager 1 could have compiled will be whatever it has already compiled. And what it has already compiled is this. The interstellar medium is denser and more magnetically complex than the models predicted. The heliopause is not a clean boundary. It is a region, possibly a layered one, where solar influence fades rather than stops. The heliosheath is turbulent in ways the simulations didn't capture. The magnetic field at the boundary maintains its solar orientation longer than it should. And the galactic cosmic ray environment just beyond the heliopause rises sharply in a way that has implications for future human deep space travel. The radiation environment outside the solar system is significantly more hostile than models built from Earth-based observations suggested. I've been thinking about what it means that we had this object out there, measuring for 50 years, and the data still surprised us. Not because the instrument failed, not because we weren't paying attention, but because the universe at that distance was simply different from the universe we had imagined at that distance. The next question for Voyager 1 is this. What exactly is the heliopause, and does it behave the same way in all directions? We have one data point. Voyager 1 crossed in one direction, roughly northward out of the plane of the solar system in the direction the Sun is moving through the galaxy. Voyager 2 crossed in a different direction, southward, in 2018. The heliopause it crossed was closer. Voyager 2 crossed at a distance of about 18 billion kilometers from the Sun, roughly 2 billion kilometers closer than Voyager 1's crossing. The plasma density and magnetic field behavior at Voyager 2's crossing were different in detail from Voyager 1's. This suggests the heliopause is not symmetric. The solar system's boundary is not a sphere. It is more like an elongated bubble, compressed on the side facing the direction of travel through the galactic medium and extended on the opposite side. This is actually what the models predicted. The shape was right, the distances were roughly right, the asymmetry was anticipated. And yet the specific plasma densities, the specific particle energy spectra, the specific magnetic field orientations at the crossing points, all of these differed from predictions in ways that the models are still being revised to accommodate. The broad prediction held. The fine structure did not. The scientists working with the Voyager data are not hiding this. The papers are public, the data is archived, the discrepancies are documented in the literature. What gets lost in the public narrative is the gap between "we cross the heliopause," a true statement, and "we understand the heliopause," which is a significantly more complicated claim. Understanding requires prediction. Prediction requires a model. The model is wrong in ways that are published, documented, and currently unresolved. Voyager 1 is the only object humanity has ever sent into interstellar space while still receiving data from it. There is no second data point in the interstellar medium. There is no cross-check, no redundancy, no ability to verify the measurement by comparing it to an independent observation. Voyager 2's crossing provides a second point at the heliopause, but both spacecraft are moving in a tiny cone of directions compared to the full solid angle of space surrounding the solar system. The interstellar medium in other directions could be dramatically different. We have no way to know. Every conclusion drawn from Voyager 1's interstellar data carries an implicit uncertainty that cannot be reduced by better analysis of the existing data. It can only be reduced by sending more spacecraft. And no spacecraft currently planned or funded will reach the heliopause in less than several decades. The next interstellar probe mission, if it happens, is a concept that has been studied but not approved, designed but not funded, hoped for but not built. In the meantime, we have what we have. One spacecraft, 47 years of travel, 22 hours of signal delay, and a dataset that continues to revise our picture of the solar system's boundary. The data Voyager 1 has returned from interstellar space represents a sample of a region that is roughly the size of a pinpoint on a map the scale of the galaxy. We have measured one tiny patch of the medium between stars. We have found it different from what we expected, and we do not know whether that difference is local, a feature of this particular region of the interstellar medium shaped by recent stellar events in the Sun's galactic neighborhood, or whether it is representative of interstellar space generally. The question that cannot be avoided, after everything this spacecraft has shown us, is not where is Voyager 1? We know that to within a few hundred kilometers, but what it is passing through and whether the environment it is sampling is the edge of the solar system as we imagined it, or something stranger, something our models have not yet found the right language to describe. We know exactly where Voyager 1 is, to within a few hundred kilometers, and we have no idea what it is moving through.